Hi everyone, I'm Tejas Satyamurthy,
I'm Adrian Monahan.
And I'm Ali Shah.
and our project focused on predicting and classifying the expected damage from an earthquake through machine learning. So the problem is that earthquakes cause an estimated $4.4 billion in economic damages each year, with millions of people being affected. And assessing earthquake damage can take a long time, several days to weeks. So there's a need for a more efficient and effective method to estimate the monetary amount of damage, to quickly allocate resources and restore and fix damages for recovery after an earthquake. So the significance of this is that it opens pathways into developing better and more efficient recovery plans and allocation of resources for prevention and safety measures for addressing post-earthquake impacts. This could lead to more insights about the areas that are most at risk in terms of infrastructure and areas that are most likely to be damaged. So some of the research questions are what the most important features and factors are in predicting total damage in an earthquake, and how the prediction changes when classifying binary to non-binary, whether damage occurs or not, versus classifying if the damage is low, medium, high, etc. And from the set of machine learning algorithms, which one is best for predicting and classifying total damage? And in broader terms, are there any strong or significant relationships between each of the feature variables? So our data set was obtained from NOAA with a collection of descriptive features about time, occurrence, metrics of intensity, and outcomes such as injuries, etc. The data set after cleaning consisted of 5,788 samples with 12 selected features. The target variable was total damage description, which expressed damage on a scale of 0 to 4, the dollar amount such as none, low, medium, high, etc. And we added a second binary target variable to determine whether or not damage occurs, so it's 0 or 1. So the algorithms we used were k-nearest neighbors, support vector machine, logistic regression, naive Bayes, and decision trees for the above reasons.
So here we have a couple of visualizations describing our data. This first is a pair of subplots describing the distribution of our target variable. On the left is a histogram displaying the distribution of the non-binary variable, which is total damage description on a scale of 0 through 4. And the one on the right is the histogram of our binary variable, which is 0 if damage did not occur and 1 if damage did occur. Here we have a scatter plot describing the relationship between two of our feature variables, magnitude and MMI intensity. And as we can see, there's a positive correlation between the two. As magnitude increases, so does MMI intensity. This next scatter plot is a description of the relationship between magnitude, our feature variable, and total damage, our target variable. We initially thought that magnitude would have a much higher impact on the target variable, but there's actually a very weak correlation between the two. And here we have a bar graph describing the relationship between total damage description and the total death description. As total damage increases, so does the average total death description, which shows the impact of earthquake damage, as there is a high monetary cost associated with the high social and humanitarian cost.
So after we performed recursive feature elimination and min-max scaling, we can see clearly that k-nearest neighbors provide the best accuracy on the test data out of all algorithms. Decision trees performed very well in the training data, but poorly on the test accuracy due to severe overfitting. Based off these results, we decided to train and optimize our models using with the k-nearest neighbors algorithm. So after the RFE previously stated, latitude, longitude, total depth description, and year were found to be the most important features, the four most important features. And after optimizing our k-nearest neighbors algorithms for both binary and non-binary classification, it was found that the best distance metric was the Manhattan distance metric, the number of neighbors being 13, and the feature weights being uniform. We also compared the a multi-layer perceptron classifier on the binary target variable to compare the two MLP and KNN. After optimizing, it was found that the best solver was LBFGS, hidden layer size of 10 and 5, and an activation of 10H. We can see that the MLP performed better on the test than the KNN as well. However, we decided that the k-nearest neighbors was a better model than MLP. It had the highest initial accuracy of the 5 initial algorithms. It had slightly less accuracy than MLP. However, it had a slightly higher recall than the multi-layer perceptron, which means that it's more likely to predict a false positive, which we believe is important, or not important, but good when predicting occurrence of damage. We don't think that our models were able to predict the extent of earthquake damage, the non-binary target variable, due to such a low accuracy. We are potentially able to predict the occurrence of damage. The binary target variable, both KNN and MLP, had about an 80% accuracy, and it would give it a good idea of who would be at risk. And some room for future work is definitely there. We could find a more complete and larger data set, as there are many values missing in the original data set. And we could also further optimize the models, or optimize the models before we compared them, as we did not do that originally.